Alright, well class, today we're going to continue our discussion on section 3.1, which tends to take a little while to get through, but this is part B I'm calling, and it's on what we call the derivative function. Now to start, I'm going to just introduce the definition of the derivative, and basically the derivative of f of x at x equals a is the instantaneous rate of change of f of x at x equals a. So the derivative and the instantaneous rate of change are actually the same thing. Okay, just different names for the same thing. And we have this notation here, which we call f prime. Okay, so f prime, that's what that sort of tick mark thing there is. F prime of a, so that's the derivative at a, okay, of f, is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. Right, same thing as the instantaneous rate of change at x equals a, but I'm tired of saying instantaneous rate of change and writing it every single time I want to talk about this. So the name derivative was developed. Okay, now what we're going to talk about today is the derivative as a function of x. So if you recall, last time, in the last lecture, we had this height function of the rock, right? And we went through and we calculated s prime of 1, I believe it was. So we cranked out this limit here, right? The limit as h goes to 0, s of h 1 plus h minus s of 1 all over h. And we did a bunch of work and got down to negative 16, if I'm remembering that correctly. Right? I probably have some of the work sitting around here somewhere. But now, let's say, right, we did all that work. Let's say now that I wanted you to find s prime of 2. Right? If I did, that means you would have to go through all this work again. You would have to crank out the limit as h goes to 0 of s of 2 plus h minus s of 2 all over h. And you would have to plug 2 plus h in, blah, 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 crank it out. And then I said, all right, now I want to find s prime, or the instantaneous rate of change of s at 3, and then at 3.5. and then at, let's say, 3.2. And every single time this happened, you would have to crank out this limit. And if you did that, you would start to see that it's basically the same steps over and over and over again, just with different numbers. And so it would become a very tedious process. What we're going to do instead is develop what we call the derivative function. So basically, we can just create a function. If we have a function f, and we can take its derivative, right? We can calculate the derivative at any particular x. We can create a new function from those derivatives. Okay, so given a function f of x, its derivative function, or the derivative function, f prime of x, is defined as basically f prime of x at any particular x is just going to be the derivative of f at that x, right? So if we go back to our limit definition, this is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, and we can define this for any x where this limit exists, right? And so now we can actually develop an entire function of derivatives. Okay, so let's say we did that with that previous example we started with. say I had that s of t was 100 minus 16t squared, right? That's the function we looked at last time. And now, instead of finding the instantaneous rate of change at, say, 1 second or 2 seconds or 3 seconds, I just find s prime of t, right? I go to find the derivative function as a function, not just at a particular value, but any value, right? So this will give me the limit as h goes to 0 of s of t plus h minus s of t all over h. Okay. So now, when I plug t plus h into s, I'm going to get, and let's not forget my limit signs, this will be the limit as h goes to 0 of, will be 100 minus 16 times t plus h squared. And actually, let me make these brackets just so it's clear. Minus, now it's just going to be s of t. In this part, we just copy down what s of t is. And in fact, you do this enough times, you'll start to realize that all you're really doing is that second part, you're changing the signs of s. Okay, and this is all over h. Then we get down to the limit as h goes to 0, okay, of 100 minus 16 times t squared plus 2th plus h squared minus 100 plus 16t squared. Right? And we see here that the 100s cancel. I've said that before, that should always happen. Your constant term of your function at this point should always disappear. And actually, everything should pretty much disappear except for your h terms, right? Because when we distribute this negative 16, you get negative 16t squared minus 2th, oops, sorry, not 2. You distribute these 16, so you get negative 32th minus 16h squared plus 16t squared, and check that out, the non-h terms vanish there. And we get that over h. And I'm going to go ahead and factor out the h in this step so that I get the limit as h goes to 0 of h times negative 32t, okay, minus 16 all over h. And the h's cancel, so we get the limit as h goes to 0 of negative 32t minus, I've forgotten h over here, sorry, minus 16h, and the h term is going to go to 0. Right. So now we get that this is equal to negative 32t. Okay, so I think I misspoke earlier when I said that we found that s prime of 1 was negative 16. We actually found it was negative 32. Sorry about that. But what we've basically found is that s prime of t, right, so s of t was 100 minus 16t squared. We have here that s prime of t is negative 32t. Okay. Now, from here, I can find tons of values, right? S prime of 0 is 0. S prime of 1 is negative 32. Right? S prime of 0.5 is negative 16. S prime of 10 is negative 320. S prime of pi is negative 32 pi. You get the idea. I can actually calculate now the instantaneous rate of change, or the instantaneous velocity, at any value I want very quickly. So I don't have to do this work all over again. I can do it once in terms of t, or once in terms of x, and we've got it, right? It's finished. We do all that work once, and then we have a function that we can actually plug values into. Okay. Now, from here, though, right, what I want to talk about is if you look at the definition of the derivative function, right, it's given in terms of a limit. And we know that limits don't always exist, right? Limits don't always exist. Therefore, since the derivative is just a limit, always remember that. The derivative is nothing more than a limit. It's a very specific type of limit. But since limits don't always exist, that means that derivatives don't always exist. Okay, and so we're going to look now at what we look for to check to see whether derivatives exist or not. It's basically checking the limit. All right, so if the derivative of f of x exists at x equals a, in other words, if f prime of a exists, then we say that f of x is differentiable at x equals a. All right, in other words, if the derivative exists, it's differentiable, able to take the derivative, okay? Or able to differentiate. That's what we call taking the derivative, is to differentiate. So we're able to differentiate f at a, we say it's differentiable, okay? And the first way to check if something is not differentiable, right, is basically if f of x is not continuous at x equals a, then it is not differentiable there either. Okay, so basically that's the first thing you look for. Now, if the function is not continuous, say you have a jump there or a hole, you can't take the derivative there. So that's a quick way to determine that. To give you a quick example of that, let's say that f of x is equal to 1 over x. And we know that this is not continuous at x equals 0. Right? And if we try to actually take the derivative of this function at 0, well, right, that's the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. So we get the limit as h goes to 0 of, well, this is basically just f of h, right? So that would be 1 over h minus 1 over 0 over h. And this is undefined. So the whole thing, it becomes undefined. Right? So 1 over x is not, let me actually write the 1 over x, is not differentiable at x equals 0. Okay. It will be differentiable everywhere else. Okay. Now, you might be thinking, all right, well, if the function f of x is not continuous, then at x equals a, then it's not differentiable. That's fine. So that means if a function's continuous, then it's differentiable, right? And the answer is wrong. This does not necessarily true in the opposite direction. Okay. So keep in mind that continuous does not necessarily imply differentiable. Okay. And I can show you an example very quickly of why that is true. Consider the function, the absolute value of x. Right, this is a very typical Calc 1 problem, right? Pretty much everyone looks at. So, say we have the absolute value, and it looks like a v, for those of you who don't remember its graph. Now, f prime of x, that will be the limit as h goes to 0 of f of x plus h minus f of x all over h. And that's going to be the limit as h goes to 0 of the absolute value of x plus h minus the absolute value of x all over h. Okay. Now, the specific place I want to look at, right, is I say that this thing is not differentiable at 0. So if we go to check f prime of 0, this will be the limit as h goes to 0. We're just going to put 0 in for h. So this will be the absolute value of h minus the absolute value of 0 over h. So we get down to this limit here, the limit as h goes to 0 of the absolute value of h over h. Now this should probably look very familiar. Okay? Probably look very familiar to you guys. Probably the first limit worksheet we did, you had a table where you looked at this one. And what I'm going to do here is analyze this on two sides. I'm going to look at the right, so the limit as h goes to 0 from the positive side, the absolute value of h over h. Now, that means I'm putting in positive values into the absolute value, and that means that the absolute value just doesn't really do anything, right? You put a positive into the absolute value, it just leaves it positive. We get h over h, which I should write the limit sign again. We get h over h, which is the limit as h goes to 0 from the right of 1, and that's just 1. Okay. All right, and then if I look at the limit as h goes to 0 from the left of the absolute value of h over h, well, now I'm putting negative values in for h. And what does the absolute value do to negative values? Well, it makes them positive. So how we can write that algebraically is by saying that this is going to be the limit as h goes to 0 from the left of negative h, right? This is a negative, so negative negative is going to be a positive. Well, that ends up being the limit as h goes to 0 from the left of negative 1, which is now negative 1. So we see that the limit from the right and the limit from the left do not match. They're not equal. Therefore, this limit here, the absolute value of h over h, the two-sided limit, does not exist. Therefore, the absolute value of x is not differentiable at x equals 0. And basically, anytime you see a sharp turn like this, right, the absolute value has a spike or a sharp turn, anytime you see that, that is going to mean that the function is not differentiable there. Okay. So, and the reason for that is basically here, a nice turning point at the very place where it turns, it's actually quite easy to draw a tangent line there. Okay. When you have a spike, well, when you go to draw tangent lines here, they're going from positive, positive slope, very steep, then suddenly they jump down to negative, right? There isn't the smooth change like we have here. Right, here we have a very gradual, it's positive, but it slows down to 0 and then starts to become negative slopes. Here it's just, it gets steeper and steeper and steeper, and then suddenly the tangent lines become negative, right? It's that sudden drop, that sudden change. So a spike or sharp turn in a graph basically implies the function is not differentiable. Okay. Oops, sorry. Okay. And then there's one final case that we need to look at. And that one's a little less obvious, or a little trickier, but let's consider the following example. Okay. Let's look at f of x equals x to the 1/3. So that's the cubed root function, right? Looks something like this. And we see that this function's continuous everywhere, and that was something to note about the absolute value, right? This function's continuous everywhere, but it's not differentiable at 0. So continuity does not imply differentiability. Right? But here, this function's continuous everywhere, right? And it's fairly smooth, right? There's no spike or anything like that. But if I look at the derivative at 0, right? So let's look at f prime of 0. So that will be the limit as h goes to 0, okay, of f of 0 plus h, so that would just be f of h, minus f of 0 all over h. Okay, so this will be the limit as h goes to 0 of h to the 1/3 minus f of 0, which is going to be 0 to the 1/3. So that's just going to go away, all over h. All right, so we have the limit as h goes to 0 of h to the 1/3 all over h. Okay, which, when you subtract, right, that's going to be the limit as h goes to 0 of h to the negative 2/3, right? That would be h to the 1/3 minus 3/3. Otherwise known as the limit as h goes to 0 of 1 over h to the 2/3. And if I just plug this in, we get 1 over 0. Okay, now, we've got to be careful here. What is 1 over 0? 1 over 0 is a plus or minus infinity case. Now, let's think about what the derivative actually is. Remember, the derivative is the slope of the tangent line. We talked about that last time. Okay, so it's the slope of this line, this tangent line, and we just found that that equals a plus or minus infinity, right? It's an infinite slope, or it's a 1 over 0. What kind of lines give us a slope of a constant over 0? Vertical lines. Okay. So that means that at 0, x to the 1/3 has a vertical tangent line. Okay, so let me draw this again. Okay, if I were to make a tangent line at 0, it does look like it would hug the y-axis there. You have a vertical tangent line there. Okay, so that's another place, a vertical tangent line implies not differentiable, even though this is continuous. All right, and this is where a lot of people have trouble with calculus, because we're starting to look at some really kind of abstract ideas here, right? And this is one of them. So if I were to just give you a graph of some kind, say we have this, and I don't know, we get a spike, then say we have what looks to be a moment of the function being vertical. Okay, so I would say that the function is not differentiable here. Or here, because it looks like we have a vertical tangent line. Okay, and then if I said, okay, say there's a hole in the graph, it's also not differentiable here, right? Because the function's not continuous there. Right, so maybe if I gave another graph, all right, say we have an asymptote here, and something like that, then something like that. Now, whenever I draw stuff that looks like this, it doesn't actually, it's not actually vertical. Okay, it doesn't fail the vertical line test, but it does look like it might for a moment. Okay, so if this were A, this were B, and this were C, well, I would say that f is not differentiable at x equals A, B, and C. Why? Well, not continuous. All right, we have a jump discontinuity. Here, not continuous. Right? That's an asymptote. And here, this is a vertical tangent line. Okay. So those are the analytical ways to find where a function is not differentiable. You basically just check the limit to see if it exists. And then graphically, you're looking for, well, basically, if you have a vertical tangent line, I forgot to write the line there. If you have a place where the function is not continuous, or the graph has a spike, or cusp is what they call it, or a sharp turn, right? This would not be differentiable. So at each spiky turn, function would not be differentiable. But if you have a smooth turn, right? A smooth turn, this is differentiable. And in fact, if a function is differentiable on a set, we call the function smooth. Right? So if a function is differentiable on, let's say, a to b, for example, then we say it is smooth, or it is a smooth function on a to b. Which, if you look at this and this, that kind of makes sense. A function is only differentiable if its graph is smooth, right? It's has a nice curvature, whereas here, I almost said that a function is smooth if it has nice curves. A function is differentiable if it's smooth, whereas it has sharp turns, not differentiable. It has spikes, not differentiable. Now this is a little misleading because that does look smooth, but remember there is a vertical tangent line there. Okay. All right, so all this talk of finding tangent lines and whatnot, let's actually look at an example where we find a tangent line. Say we find the equation of a tangent line. So you need two things to find a line. Right? Two things to find a line. If you remember, you need a point. Well, you either need 2 points, but if you need an equation, you need the slope and a point. Okay. Well, I suggest, or I submit that we already have the point. Okay. If when you graph this guy, and it's going to look something like this. And we're looking at the tangent line. That's sort of to scale. Tangent line going through this point at x equals 1. Well, if I wanted to find the y value, right, this is, well, the point 1, f of 1. And f of 1, when I plug 1 in, is going to be 4. So this is the 0.14. Right, so we have the point. Right, we have that piece that we want. Okay. What we need now is the slope. Right? And how do we find the slope? Well, what is the slope of the tangent line? And I could draw. Oh God, I could draw that tangent line for us. How do we find the slope of that tangent line? Well, at x equals 1, the slope is going to be f prime of 1. Okay. Now we could find f prime of x to start with, and actually that's what I'm going to do, because let's say I also wanted to find the equation of the tangent line at 0, or maybe at -2. Okay. If I wanted to do those things, I would have to do all this work all over again. So first I'm going to find f prime of x. And this is actually a good way to go about doing problems like this. Even later when we get tricks that will help us do this faster, you don't want to really ever just jump right to f prime of 1. You want to find f prime of x. So this will be the limit as h goes to 0 of f of x plus h minus f of x all over h. And this also helps us give us another example of finding the derivative function the long way. So this will be the limit as h goes to 0. And you know what? I might want to give myself a little bit more room up to the side here. So f of x, if you remember, was x squared plus 3x. All right, so that's going to be, I'm going to put x plus h in, so that's going to be x plus h squared plus 3 times x plus h, so that is my f of x plus h term, minus, okay, now I'm going to just subtract f of x, which was just x squared plus 3x, all over h. So we get the limit as h goes to 0. Now we expand this guy out to get x squared plus 2xh plus h squared. Expand this guy out to get 3x plus h. And then this negative sign affects both pieces to give me negative x squared minus 3x. So I have that all over h. And a bunch of things cancel, right? The x squareds cancel, the 3x's cancel, and we are left with just h terms. Okay. Oh, and again, I did that again. That should be 3h there. Okay, we're left with just h terms. So I'm going to go ahead and factor the h on this step. So I get h times 2x plus h plus 3. The h's cancel, so this actually ends up being the limit as h goes to 0 of 2x plus h plus 3. The h goes to 0 and everything else pretty much stays right there. So we actually get 2x plus 3. So that's f prime of x. So let me write that on our original problem here. F prime of x was 2x plus 3. So f prime of 1, I'm just going to plug 1 into that. I get 5. So the slope is 5. And I want to check what I have over here. Does it look like this is a slope of 5? Well, it's positive and fairly steep. So actually that looks pretty accurate. Okay. Okay. So now that I have the slope and I have a point, well, if you remember, the equation of a line is y equals mx plus b, and we're going to plug in the point, we're going to plug in the slope, and solve for the y-intercept b. So the point was 1, 4. So I have that 4 is equal to m, which is the slope 5, times the x value, which is 1, plus b. So this gives me that b is going to be -1. So the equation of this line here, I'll write it in red, y equals 5x minus 1. And that does look kind of accurate. I didn't draw this to scale at all, but I did get a negative, what looks to be around -1 down here for my y-intercept. Okay. And then if I wanted to find, let me make this a little better. Let's say I wanted to find the equation of the tangent line at -2. Okay. So let's do that. So now I'm going to find the equation of the tangent line. At x equals -2. Okay. Well, once again, -2 is about right here, I guess. We already have the point, right? Because the point is going to be -2, comma f of -2. All right, and when you plug -2 into here, we're going to get 4 minus 6. So that will be the point -2, comma -2. All right, so 4 minus 6. All right, let me go ahead and draw that tangent line while we're at it. It looks like it's something like this. So I should probably get a negative from this graph. I should get a negative tangent line, and the number should be less than 5, since this looks shallower than that 5. So let's see here. We have the point, right? The point is -2, comma 2. Now we just need to find the slope, and the slope is going to come from f prime of 2. Now, since we did that work to find f prime of x, which is 2x plus 3, I'm just going to plug that in here. All right, that's going to be 2 times -2 plus 3, so that's -4 plus 3, which is -1. All right, so that's my slope. And that looks about right. I mean, it's negative, it's shallower than 5, right, less than 5. So let's see what we get here. Remember the equation of a line, y equals mx plus b, and we're just going to put all of our information into it. Y value is -2, m is -1, x is -2 plus b, and I get -2 is equal to 2 plus b, giving us that b is equal to -4, which from the graph looks about right. It looks like -4 is about right there. I'm showing you this because there are lots of ways to check your work as you go along, right? Lots of ways to do that. Just a matter of remembering where they are and checking your work. If you get an answer that doesn't make any sense, that doesn't mean like fix it. I mean, that doesn't mean like brute force it. That's what I really mean. Say you got a +4 here and that didn't make any sense. Some people would just change that to a negative and think I wouldn't notice. What it actually means is you did something wrong up here and you need to go back and check and see what that was. Okay? Don't just try and, force your way through it. Okay. All right, so now that we have this, the equation is y equals, the slope was -1, so that will be -x minus 4. Okay. Now, when you start doing this enough, you'll start to see a pattern. Okay, and there's actually a formula that we can use that simplifies this process a lot. Basically, the equation of the tangent line at I should say of f of x at x equals a is given by, okay, it's going to be y is equal to, okay, it will be f prime of a times x minus a plus f of a. You might think, well, really? Are you sure? And the answer is, well, yeah, of course. Say the first problem we had, at x equals to 1, right? For the first example, okay, we had x equals 1 is what we were looking at. So the equation from this would be y equals f prime of 1 times x minus 1 plus f of 1. Well, f prime of 1 we found in that first example was 5, so I put that in, times x minus 1 plus f of 1, and that we found almost immediately was 4. Right, and you distribute that 5, and you get 5x minus 1, which is exactly what we got here. For the second example, we had that x was equal to 2. And from this formula, that would mean that y is equal to f prime of 2 times x minus 2 plus f of 2. Right? A is going to be our 2. Okay. So f prime of 2, we calculated there was -1. Right? Times x minus 2 plus f of 2. F of 2 we found was -2. So we distribute this -1, so I get -x plus 2 minus 2 is equal to sorry. Typo. -2, right? So when it becomes x minus 2, that's x plus 2. My bad. I knew something didn't look right. So when we distribute that -1 now, it becomes -x minus 2, so that's -x minus 4, which is exactly what we got before. Okay, so some people like to just have this formula memorized and just plug everything in, get the values. Some people, on the other hand, just prefer to actually use this y equals mx plus b and solve for b. And there are, other ways to do it as well. You just use what you know about finding lines, right? Finding the equation of lines. Okay. That's pretty much what there is to section 3.1, except now calculating or finding derivatives using limits. Okay, and I plan to have another extra examples to kind of go through a couple more examples of that. All right, so until then, cheers.